In this lecture, we're going to consider a common problem, the titration of a mixture where both components of the mixture react with the titrant. When we run into this problem, we can determine which solid product precipitates first by comparing the KSP values if the dissociation stoichiometry matches. That is, do the solid products that form have the same Van Hoff factor? If the Van Hoff factors are different, say one product is made of 2 ions while the other one is made of 3, then we have to solve for the molar solubility to determine which solid precipitates first. Recall that having a smaller KSP or a smaller molar solubility means that the associated product will precipitate first because it takes a smaller concentration of ions in solution to achieve a saturated solution that allows the excess ions to precipitate, forming the solid. Now, just like the last example we saw from Lecture 6-4, we can use the endpoints of each precipitation to determine the concentration of cations remaining in solution. To see how that works, let's look at an example where we have a solution containing iodide and chloride, and let's titrate it with silver ion. Here we've written out the two balanced chemical equations for the solid products as they dissociate into their component ions. The law of mass action allows us to rewrite both equations as KSP expressions. Before we decide which solid precipitates first, we need to answer the question, can we compare the KSP values directly, or do we need to solve for molar solubilities? Both silver iodide and silver chloride have Van Hoff factors of 2. Meaning they dissociate into the same number of ions, 2 each. For this reason, we can compare KSP values directly. So, which KSP value is smaller? We see that the KSP for silver iodide is the smaller of the two. Which solid precipitates first? Because the KSP for silver iodide is smaller, that's telling us that it requires a smaller concentration of ions in solution to achieve equilibrium. When we achieve equilibrium, that means we have a saturated solution. As soon as that equilibrium concentration of ions is exceeded, the solid will precipitate out, leaving behind a saturated solution of silver and iodide ions. Now, chemists are very fond of graphing their data, so let's do that on the next slide to see what else we can discern from the titration data. If we look at this diagram, we can see that we have two distinct endpoints as indicated by the steep decrease in the titration curve, here and here. The first endpoint occurs at the end of the white region when the solubility product for iodide and silver exceeds our KSP of 8.3 times 10 to the 7th. We're detecting this endpoint with a silver electrode, which is sensitive to the sudden increase in free silver ions that results once most of the iodide has precipitated out, but before the chloride begins combining with a sudden excess of silver. If you're trying to trace this curve, it's labeled B, here and here. And the endpoint occurs once 23.76 milliliters of silver ion has been added. The blue region represents silver ion combining with chloride as we follow the path of titration curve A. Let's see, A is here and continues here. We see the chloride endpoint occurs after a total of 47.71 milliliters of silver ion solution has been added. When finding the amount of silver ion needed to precipitate out the chloride, which volume should we use for the calculation? This one, or some combination of the two? Did it take all 47.41 milliliters to precipitate out the silver chloride, or did some of that volume get used up in the iodide titration? We see that to calculate the amount of silver ion needed to precipitate out the chloride, we have to take 47.41 milliliters and subtract the volume needed to complete the iodide titration. Let's look at a sample calculation to make sure we're understanding the process. 40 milliliters of an unknown solution containing iodide and chloride was titrated with 0.0845 molar silver ion solution. What is the concentration of each halide in the original unknown solution? The calculation for the iodide endpoint is pretty straightforward. I tend to set up my calculations so that I can cross out all of the units to make sure I'm doing it right. Here I've got the molarity of the silver ion solution in terms of moles of silver per milliliter of solution, so I can multiply by the amount of silver ion solution without having to convert to liters of silver ion solution. This is simply a personal preference. Please find the method that works best for you and stick to that method, as long as it continues to give the right answer. Next, we use a mole-to-mole ratio to go from moles of silver to moles of iodide. Then we divide by the volume of the unknown solution to get the molarity of iodide. Given this problem setup, how many significant figures should we claim? We are limited to 3 significant figures due to the molarity of the silver ion solution. 1, 2, 3. Therefore, if we want to include an uncertain additional digit, we need to be sure to subscript it. How about the chloride endpoint? What's our first step? The first step requires us to subtract the amount of silver solution required to reach the iodide endpoint, to be subtracted from the total volume used for the entire titration. So right here. Next, we set up the problem as before, noting that if we want to retain an additional uncertain digit, we can do so as long as we subscript the number. That's all for now.